Welcome to the Explainer. I am absolutely thrilled to have you here today. All right, let's just dive right into it. Today, we're basically transforming this session into a rigorous, high-yield bootcamp for CISSP Domain 3. We're going to master the public key infrastructure and those core cryptographic applications that are just absolutely essential for passing this exam. Our goal? To break down the heavy complexities of cryptography so you can spot those tricky, incredibly common exam traps from a mile away. Here is our roadmap for today. We'll start with asymmetric basics, followed by hashes and signatures. Then we'll decode PKI, explore applied hybrid cryptography, and wrap it all up with cryptographic attacks. Starting off with Section 1, Asymmetric Cryptography Basics. So we all know symmetric cryptography is blazing fast, right? But it has this massive, glaring hurdle: secure key distribution. I mean, how do you securely share a secret key with someone you have literally never met? Well, asymmetric or public key cryptography was designed specifically to solve that exact problem, but it introduces what we call the which key dilemma. So time for a CSSP exam mindset note. You need to memorize these golden rules. To encrypt a confidential message, you use the recipient's public key. Why? So only they can decrypt it with their closely guarded private key. On the flip side, if you want to digitally sign a message to guarantee non-repudiation, you use your own private key. That way, anyone can use your public key to verify that it actually definitely came from you. Confidentiality uses the recipient's public key, non-repudiation uses the sender's private key. Now, you might be wondering about key sizes. Well, not all bits are created equal, and key length varies wildly across different algorithms. To give you a sense of scale, to achieve the exact same level of cryptographic strength as a 128-bit symmetric key, you would need an RSA key that is a whopping 3,072 bits long. But check out elliptic curve cryptography, or ECC. It only requires a 256-bit key to match that exact same level of security. ECC uses what's called the discrete logarithm problem to achieve massive security with incredible efficiency, and that is exactly why it's heavily favored for mobile phones and low-power devices. Moving right along to Section 2, Hashes and Digital Signatures. Okay, so a hash function takes a potentially massive message and generates a unique fixed-length output value called a message digest. Think of it like a digital fingerprint. It has to be one-way, meaning it's mathematically impossible to reverse engineer the original message from the hash. And it must be collision-resistant, meaning no two distinct messages should ever produce the exact same hash. For the exam, you absolutely must have these hash value lengths committed to memory. MD5 is 128 bits. SH1 is 160 bits. Now notice that SHA-256 obviously produces a 256-bit digest, but here is a highly testable fact you cannot miss. SHA-256 actually processes the message using a 512-bit block size. Do not let the exam trick you by confusing the output length with the block size. Oh, and also note that Havel can produce variable lengths anywhere between 128 and 256 bits. Let's step through the exact step-by-step logic of creating a digital signature. Step 1. Alice generates a hash, or message digest, of her plaintext message. Step 2. Alice encrypts only that message digest using her own private key. That encrypted digest? That is the digital signature. Step 3. She appends that signature to the plaintext message and sends the whole package over to Bob. When Bob gets it, he'll decrypt the signature with Alice's public key, generate his own fresh hash of the plaintext message, and compare the two. If those hashes match perfectly, Bob has proven both integrity and non-repudiation. Which brings us to another really critical CISSP exam mindset note. Remember this rule for test day: signatures alone do not encrypt the main message. A digitally signed message is usually sent in plain, readable text, with the signature just appended at the bottom. If you want confidentiality alongside your integrity and non-repudiation, you have to add a completely separate step of encrypting the entire package with the recipient's public key. Basically, never assume a signature provides secrecy. Section 3. Public Key Infrastructure, the Hierarchy of Trust. So, how do we actually trust that a public key belongs to the person claiming it? That's exactly where PKI comes in. Through trusted third parties called certificate authorities, or CAs, we can confidently validate the identities of individuals or web servers we have never communicated with before. The mechanism that makes this trust possible is the digital certificate, which is governed by the X.509 standard. When you look at one of these certificates, it contains the version, serial number, who issued it, and its validity dates. But the absolute meat of the certificate, the most important part, is the subject's public key. The entire point of the CA digitally signing this certificate is to endorse that specific public key and directly tie it to the subject's verified identity.
Now, sometimes certificates need to be revoked way before they expire. Maybe a private key was compromised, right? Historically, we used certificate revocation lists, or CRLs, but constantly downloading these massive lists introduced dangerous network latency. So the industry moved to the Online Certificate Status Protocol, or OCSP, which checks validity in real time. Better, but OCSP placed a massive, crushing burden on the CA's servers. So what's the brilliant modern solution? Certificate stapling. The web server itself securely gets a time-stamped, signed OCSP response from the CA and essentially staples it to the certificate it hands to the user. This is an incredibly clever trick because it completely removes the burden from the CA while still maintaining real-time security.
All right, Section 4, Applied Hybrid Cryptography.
We know asymmetric cryptography is fantastic for secure key exchange, but terribly slow. And symmetric cryptography, blazing fast but terrible for initial key exchange. Hybrid cryptography brilliantly combines the best of both worlds. We use asymmetric crypto just long enough to securely exchange a temporary random symmetric key. We call this an ephemeral key. Then we switch to that fast symmetric key for the actual bulk data transfer. The most famous example of this is TLS, which secures our web traffic. When a client and server connect, they have to agree on a cipher suite. When you encounter a cipher suite string, you need to be able to read it like a sentence for the exam. Let's break one down. TLS is the protocol. DHE is a key exchange algorithm. RSA handles the authentication. AES_256_CBC is the fast symmetric bulk encryption. And SHA-384 is the hash for integrity. Now, the absolutely crucial detail here is the E in DHE. It stands for ephemeral. This means it generates a brand new temporary key for every single session, providing what's called perfect forward secrecy. So even if an attacker compromises the server's main private key years later, they cannot go back and decrypt past sessions.
Let's look at a fascinating application of cryptography, steganography. This is the art of hiding a secret message inside an otherwise perfectly normal-looking file. Take a simple tool like ISTEG, for example. Time for another CISSP exam mindset note. The exam isn't just going to ask what this is. They will test your understanding of exactly how this works under the hood. Steganography hides data in plain sight by modifying the least significant bits, or the LSB, of a file, like a digital image. Because it only changes the absolute smallest value of a pixel's color code, the human eye literally cannot detect the difference, but a hidden text file can be perfectly preserved inside the image data. When we apply cryptography to actual network traffic, we have to choose between link encryption and end-to-end encryption. Link encryption acts like a secure black box tunnel between two routers. It encrypts everything, including the routing headers. Because of this, the routers have to decrypt and then re-encrypt the data at every single hop just to figure out where to send it next. End-to-end encryption, on the other hand, only encrypts the payload itself. The headers stay in plaintext, which means it routes much faster across the network, though it is definitely more susceptible to traffic sniffers figuring out who is talking to who. If you want an easy way to remember this, think of IPsec. Tunnel mode is like link encryption, while transport mode is end-to-end. Finally, Section 5, Defeating Cryptographic Attacks. Malicious actors out there aren't just blindly guessing passwords. They're actively exploiting statistical flaws and implementation weaknesses to completely bypass these robust architectures. Let's look at the specific cryptanalysis techniques you must be able to differentiate on test day. First up is the chosen plaintext attack. The baseline requirement here is that the attacker actively selects the input data. They have the ability to feed a plain text message of their choosing into the encryption system, and then sit back and observe the resulting ciphertext that comes out the other end. By analyzing exactly how their specific inputs change the outputs, they attempt to mathematically derive the secret key. Now, you want to immediately contrast that with a chosen ciphertext attack. Notice how the attacker's starting material shifts here. In this scenario, the attacker actually has access to the decryption mechanism. They feed selected ciphertext into the system to see what plaintext emerges. This is a classic exam distinction. Are they starting by choosing the unencrypted text, or are they starting by choosing the encrypted text? Next is the meet-in-the-middle attack. Now, this is a highly specific mathematical attack against algorithms that use 2 rounds of encryption. The attacker takes a known plaintext and encrypts it with every single possible key from one side, while simultaneously taking the corresponding ciphertext and decrypting it with every possible key from the other side. When the outputs meet in the middle and match up, boom, they've cracked both keys. This precise mathematical vulnerability is the exact reason double DES was quickly discarded and replaced by triple DES. And here is a massive CISSP exam mindset note to keep you safe on test day. We need to actively dismantle this known test trap right now. Never, ever confuse meet in the middle
with man in the middle, which you'll also see called an on-path attack. Meat in the middle is a mathematical cryptanalysis attack against double encryption. Man in the middle, however, is a network interception attack, where an attacker spoofs a session setup, tricking both parties into communicating with the attacker instead of each other. They have similar names, but they are wildly different concepts. So what about defending against brute force password attacks? Attackers absolutely love using rainbow tables, which are these massive gigabyte-sized lists of pre-computed hash values for common passwords. To defeat them, defenders use a cryptographic salt. A salt is simply a random value added to the password right before it gets hashed. This is huge because it means the attacker has to compute a brand new rainbow table for every single salt. Furthermore, we use key stretching algorithms like PBKDF2, bcrypt, or script. These algorithms run the hash thousands and thousands of times, intentionally slowing down the process to make brute forcing computationally exhausting and totally impractical for the attacker.
Finally, let's take a quick look at the horizon. Quantum computers use qubits to solve complex factoring problems exponentially faster than classical computers. If quantum supremacy is achieved, the fundamental math behind RSA and Diffie-Hellman will be trivially broken. So here is a final provocative thought to leave you with today. Attackers are currently stealing and storing encrypted data today, just waiting for the day a quantum computer comes online that can break it open. Knowing this harvest now, decrypt later strategy exists, how long does your organization's encrypted data truly need to remain a secret? And are you already planning a transition to post-quantum cryptography? Thanks for joining me in this Bootcamp Explainer, and I will see you in the next one.